Start the recording. Great. Hi, everybody. Welcome to our webinar today, Building Resilience Using Vehicle Batteries. Today's July 10th, 2024. I'm Joe Wachunas at New Buildings Institute. Great to have you all with us. Really excited about this topic. Let's dive in. But before we do, just wanted to say this webinar was developed in partnership with the San Diego Learn program. The Learn program is a San Diego-based workforce education and training program that's partnered with New Buildings Institute and the Advanced Water Heating Initiative to offer free energy efficiency and electrification webinars. Check out their website for more info, www.sandiegolearn.com. And huge thanks to San Diego Learn. And I want to introduce my co-moderator today, or have her introduce herself, but Allison Wiley, great to have you with us, and talk to us a little bit about your electric school bus newsletter.
Thanks, Joe. It's really good to be here. Good afternoon, everybody. I'm Allison Wiley. I'm here in Oregon, where lots of us are. We're in a good sweaty heat wave that reminds us that climate change is real. The work we are all doing on electrification and resiliency is urgent and important. So thank you for engaging with us on this. I am the founder of the Electric School Bus Newsletter, and it goes out nationwide to people in all different sectors. I write it especially, though, for school bus fleets to help them navigate the move to electric. And the World Resources Institute, who you'll be hearing from shortly, has been a great partner to me in funding many of my newsletters. I am also a consultant, and I work with Joe and Karina on the Mover project. I have done a TEDx talk that dramatizes this whole concept that we're talking about today of resiliency. The Mover concept is on that topic. I'm going to share the slides. Excuse me, I'm going to share the links to my TEDx talk about community resilience and also my newsletter. I'll put those in the chat shortly. Joe, I think it's back to you.
Great. Well, yeah, thanks. Please do check out both of those resources. And all right, so today we are going to talk about using vehicles to enhance building resilience. We'll dive into what the national landscape looks like for combining electric vehicles, electric school buses with buildings to enhance their resiliency, especially when the grid is out. We'll talk about barriers that these initial projects across the country are encountering as they work to create microgrids with vehicles. We'll talk about how standards are evolving to accommodate this technology, and get into the value for communities of having microgrids with building powered by electric vehicles. We'll also do some deep dives into pilot projects and initial learnings, because we all want to see this happen, and there's on-the-ground projects trying to make it happen. And before we do that, we should level set quickly on what is a microgrid. The U.S. Department of Energy has a good definition. A microgrid is a group of interconnected loads and distributed energy resources like solar panels and electric vehicles that has clearly defined electrical boundaries. Microgrids can connect and disconnect from the grid, and they can operate while they're connected or operate while they're disconnected. And there are many different types of microgrids today. Today, we'll look at some that have resilience as their focus, others that prioritize sustainability, and all the microgrids that we'll be chatting about in today's webinar will include electric vehicles. So, Allison, I'll turn it back to you to introduce our great panelists today.
Thanks, Joe. I'm going to say I've had the pleasure of working with my co-moderator, Joe Wachunas, on several projects over several years. I now have the pleasure of introducing our four excellent panelists. And I'm going to introduce them all at once so that they can then hand off to each other. Please know we're going to reserve 20 minutes for questions and answers so that we can engage with you and have a good conversation. Please put your questions into the Q&A, and you're also free to introduce yourselves in the chat. This is an interactive session. Our first two panelists both work at the World Resources Institute, known as WRI. Specifically, they're with the Electric School Bus Initiative at WRI. First up, we'll have Gregory Kresge. He is the Senior Manager of Utility Engagement and Transportation Electrification. And he has 16 years experience of working with utilities, including with Hawaiian Electric and the Commonwealth Utilities Corporation. His deep knowledge of utilities involves renewable energy resources and electric vehicle charger deployments. Following Gregory, his colleague, at WRI is Robert Stafford, a research associate. Robert focuses on transportation electrification and grid resiliency. He earlier worked at San Diego Gas and Electric, where he was the lead designer for their electric vehicle infrastructure program. He holds an MA in sustainable energy from Johns Hopkins University. Following Robert will be Sam Hill-Crystal, who is with the Mobility House in North America. And Sam is the manager of strategy and business development. He specifically oversees my favorite segment, which is the school bus segment. And the Mobility House in general expands charging management all around the world. And Sam helps fleets to understand how charging and energy management can support their transition to electric, which is key. Earlier, he worked on fleet electrification at Optiny Inc. and at Alameda County. He will pass off to our final panelist, Karina Hirschberg, an engineer who's an associate principal at PAE. And she has over 15 years of experience with systems modeling, data analysis, electrical engineering, all of the things that I'm not smart enough to know about, but she excels at interpreting these things to other people like me. Yay. High performance buildings, renewable energy systems. She has dual roles in analysis and engineering. And she helps projects to implement regenerative and resilient solutions. She leads the development of microgrid design at PAE. Okay, so please know that we are reserving 20 minutes for Q&A. Please put your questions into the Q&A box. Please note, we will be sending out slides and recording within a couple of days to everyone who registered for the webinar. Greg, would you like to kick us off?
Yeah, thanks. I'll stop sharing. Great to have you all with us.
Unmute. Can you guys hear me and see my screen?
Yeah, looks great.
All right, amazing. Okay. With that, I'm gonna present more slides than I'm gonna be able to go through. So I'm just gonna know that I included a lot of these so that when you get the recording and you get the slide deck afterwards, that there's resources in there. There's a whole bunch of hyperlinks. Please visit our website. Most of these are available on the website. So I'm going to just jump in really quickly about WRI. We're a global think tank, sort of, global institution with employees all over the world, really focusing on sustainability, water security, food security, in addition to decarbonization of the grid. And that's where we come in also with the electric school bus initiative. We're located in all of these various countries across the world. Working basically all on very similar issues. So some more about why we're doing the work that we're doing. One of the main things is, like, we want to give all these reasons for why we're so emphatic and working so hard on the electric school bus initiative and trying to get all school buses across the nation to be electric. And a lot of that is around making sure that kids are breathing cleaner air, drivers are breathing cleaner air. We're not, we're trying to lessen the amount of emissions. Kids, especially kids and drivers that are in school buses, are exposed to 12 times the amount of emissions that they are on the outside of the bus. And a lot of school buses, especially diesel school buses, they have long idle times where they're not turned off. They're sitting there running in the near breathing environment. And there's a lot of other positive benefits that come with this. And one of them is that we'll be talking about today is resiliency. Here's some harms of diesel exhaust. This most affects disadvantaged communities. They tend to be along transportation corridors, tend to be more towards more co-located with depots, and are exposed to more of the emissions. We have a lot of resources on our website. I'm just looking through a couple of them here. Please visit wri.org. You can look at the Electric School Bus Initiative. We make all of these resources available for free. There is no charge to them. You can download any of them at no cost to you. One of the things that you'll hear about is that there's a total cost of ownership, which is looking at the whole picture of the bus. This would be looking at the cost of the bus, the maintenance and operations requirements of the bus, in addition to the diesel or the fuel that's going into the bus. And we look at these stacked value propositions of, what is it going to cost to obtain an electric school bus as opposed to, say, a diesel school bus? What does it look like after you receive certain incentives or stackable rebates or incentives? And then what is that cost savings over the life of the bus? We really see a huge cost savings in operations and maintenance of the bus, of electric school buses, because there's so many less moving parts, and you don't have all the fluids replacements and all the other things that go along with internal combustion engine vehicle. So there's a lot of momentum that has built on. Besides the Clean School Bus Program funding, which you probably have heard about, which is administered through the EPA, there are a lot of other incentive programs out there that are also helping promote electric school buses in addition to the infrastructure. So you have a lot of stackable opportunities, a lot of ability to be able to get funding to help electrify your fleet. We are working together as 5 different pillars. Robert and I sit in pillar number 3, which is that utility and funding and financing section. We work with utilities across the nation, trying to electrify these fleets and really try to make sure that there's a good knowledge transfer there between school districts and utilities. We have out a power planner. This is really kind of a step-by-step what you should consider if you're looking to electrify your fleet, when to talk to your utility, some of the questions you should ask, some of the things that you should be looking at doing. And we're getting to resiliency. So I only have a couple minutes left. So I'm going to run through these slides really fast, but basically we're talking about, in this resiliency aspect, these batteries on these school buses tend to be high capacity batteries. They're much larger than your own vehicle. If, let's say, you have an electric vehicle, a Leaf, a Tesla, whatever that is, you're talking, the capacity is maybe 8 times, 10 times that capacity on that vehicle. These buses also are not used. They have long dwell times. So when they're not being used for student transportation, they can be used for other purposes. So vehicle to grid, vehicle to X, bidirectional charging. You're going to hear a lot about these different terms. I'm providing this in the slide. You can go back through and look through this. When we talk about V to X, we're talking about, these bidirectional energy stored in the bus of the battery of the bus, and then discharged at maybe some other location or at that same site for some other purpose. Now, that doesn't have to be vehicle to grid. It doesn't mean that those electrons have to go back across the meter and back out to the lines. It can be there specifically to power a site on its own. And that's that microgrid sort of environment that we were talking about. So here's some of the benefits of the vehicle to X and using that bidirectional charging and that energy stored in the batteries. Here's some of the applications that you might hear about. There's demand charge mitigation. If you don't know what demand charge is, it's basically an adder onto your bill because you're setting a peak with your consumption. This really happens a lot with electrified fleets when they're moving from diesel fuel to electricity fuel. You have different pricing mechanisms. You can provide site power, there's demand response, frequency regulation, all these different things that are potential aspects that can be used from the energy stored in the bus for some other purpose. We look at disaster response and resiliency as all of these things that could be potentially provided from energy stored in batteries. Specifically, the green ones are what we're looking at for electric school buses, is where we feel like there might be the highest and best use. And we're specifically in the resiliency aspect, we're looking at this far left-hand side, which is the shelter component. So we're looking also at working on many different projects. We're working on projects across the country with different partners to look at schools as shelters, looking at electric school buses as being able to drive up with a school as a shelter, having the right equipment installed, the right infrastructure, load isolation, not pulling up and powering a whole campus, but are we pulling up and providing sleeping environment for shelters that would maybe use only the gymnasium or the cafeteria. Looking at providing refrigeration for people who need their medicine refrigerated, for example, like insulin or something along those lines, where once you run out of ice and you're no longer on grid power, your refrigeration possibilities go away. So here's some of the things that we view as being in these schools as shelters environments. And I'm going to run through this really quick. We have a whole bunch of resources that are out there. We can talk further about this if you have questions about some of these. These are hyperlinks. They should work when you click on them, but they are available on our website. And this is, it goes through, what is an electric meter at your site? What does that look like? What are the conversations you should be having with your utility? Can you start slow? Can you start with something smaller instead of a full build out? Do you have the electrical capacity at your site now to be able to install some form of charging to meet your immediate need? And then look at a longer term plan as you move along. So here's some of our partners. We have stated policy partners as well. And then here's my contact information. And with that, I'd like to hand it over to Bobby. Thank you very much.
Thanks so much, Greg. Really appreciate that. Bobby, as you're getting the your slides loaded, Greg, could you give maybe just a brief summary on where you see electric school bus resilience projects? Are we in the pilot? I think we are in the pilot stage, but where do you see them going on across the country, or they're just a select few spots from your birds?
Yeah, so actually we had a meeting this morning. So there's a lot of components around this. One of the things that we are working on are mutual aid agreements, which are these memorandums of agreement with different potential providers of these resources. So it's the school bus owner that would be, if they have a bidirectional bus, be able to displace a diesel generator in a disaster. They can pull up the bus and discharge energy from that bus. In the particular circumstance that we're actually forming a workshop around is getting these agreements in place before the disaster starts. These agreements are not new. This happens with other types of emergency response equipment and resources like helicopters and tents and roll-off bins and tractors and those sorts of things that would be utilized in a response. It sets up a mechanism for these resources to be able to be used when the disaster occurs, if they're available. It's no obligation if they're not available. It just sets up the avenue for somebody like me, who was in the incident command system and responding to an emergency as the resource section chief, to be like, oh, here's some electric school buses and here's a facility that's set up to receive it. So we are able to use this resource and be able to bring it in and utilize it. And then there's a compensation mechanism that goes along with that within the disaster realm, which is if it's a federally funded, disaster or federally declared disaster or state declared disaster, some of those funds are freed up to be able to utilize those resources.
Great.
Yeah. So I don't know if that helps.
That does. And it's a great segue to your.
And I was about to say, great segue. Talk more about mutual aid agreements. Yeah. So thanks, Greg, and thanks, Joe, for having me on today. So yeah, as we're talking about, right, these mutual aid agreements aren't new. They're just new to school buses, and that's one of the things that we're leading. As global warming continues to happen, situations are going to get hotter, more danger from a lot of different disasters occurring, and these school buses can be a resource there, right? This is basically a diesel generator on wheels for emergency purposes. You can move it anywhere it needs to go, but it's not going to be polluting the air near it. and it can serve transporting children when it's not being a diesel generator. These have, really predictable routes, schedules. There's a lot more funding out there, and you're not going to be transporting kids during a disaster, and so you're going to have these resources freed up. Now, this really has the possibility to do a lot of good on our electrical system and on our, emergency preparedness, our community resiliency, on top of just being a good investment in a lot of cases for these electric school buses. That said, there are a lot of people that you need to talk to in order to be able to get one of these mutual aid agreements out. There's your utility, there's first responders, county, lawyers, folks at the school, folks who are manufacturing the buses. And so it's important to get this started early. The earlier you can get this started, the more likely this is to be useful as you're planning forward in the future. So before an emergency, right, you're developing your MAA, you're identifying what you need, where you might be going, and you're talking to your community. What is this going to look like? What's a school bus going to do? Where is it going? Where can I go in an event of emergency? During an emergency, you're going to deploy that bus, make sure that it's able, right? It has a good state of charge. It's going to be useful. You're going to disconnect your system. You're going to plug in that bus, power on, and there you go. Afterwards, mostly the reverse, right? You're going to power down the bus, talk to your utilities, say, hey, we're reconnecting, put that back on. In a lot of cases, you might have an automatic transfer switch that's able to detect when utility power is coming back on. And that's really going to be a great thing going forward. One of those things that we really want to push for when we're building out these systems. And like Greg said, you can compensate the ESB operator afterwards. Or if it's, a local municipal group, that's just savings, right? Money that didn't need to go towards a diesel generator that can be recouped from the federal government. Yeah, I'd really encourage, thinking about an MAA in your space. If there's school buses around, we have guides from ESBI on this. Go to our website, find it right there. It'll be linked in these slides as well. These are some other examples of MAAs, just how they've been used in the past. And yeah, keep it simple, get it started. That's one of the best things we can recommend, is just the earlier you start on this, the better the conversation is going to be, the more money you can find for projects to be able to fund it. And yeah, I think that's the end of my slides. Contact here, please feel free to reach out to me, but I think I'm kicking it over to Sam.
Great. Yeah, thanks so much, Robert. Appreciate it. And Sam, as you come on and get your slides going, Robert, someone was asking, have you seen real world examples of folks setting up mutual aid agreements in anticipation of electric school buses?
Yeah, so Greg was saying we just had a school district and an operator in Illinois be able to enact one of these mutual aid agreements. They're not haven't been deployed in an emergency, but right, that's why you get the MAA set up, so that when the emergency comes, you can start to think about this, start to plan that. And yeah, we're really excited for what the future of electric school buses looks like in terms of community resiliency, but also just making cleaner air for those kids.
Thanks so much. I appreciate that, Robert. Well, now we'll take a look. We'll take a view. We've gone from the bird's eye view from a nonprofit leading a lot of the convening around electric school buses, and now we'll go to the on the ground view from a company that's trying to help get chargers installed and doing some innovative work on vehicle to building with chargers and vehicles. So, Sam, turn it over to you.
Yeah, thanks, Joe, and thanks, Bobby and Greg, for kicking us off. My name is Sam Hill-Crystal. I'm with the Mobility House. We are a technology provider. We're a global company, and we have a range of businesses, but in the US, we really focus on charging management software, which we think is a really important layer of intelligence in any sort of charging project, but especially in bidirectional projects. And vehicle to X projects, as Greg mentioned. So I'll go through a couple example projects that we're involved in that have to do with resilience and electric vehicles. One V2B focused project that is underway in Oakland, and then I'll share some lessons learned. This is a super broad topic, so excited for Q&A. So to continue my little intro for Mobility House, this is sort of going over our entire business globally. In the US, we're really focused on smart charging, which is the charging management system that I mentioned. So that's a software system that controls the operation of chargers. So in a vehicle to X scenario, right, we might be telling the charger, okay, now it's time to initiate a discharge from the vehicle based on some signal we've received from the utility, or the fact that building's been isolated from the grid and needs backup power, something like that. And really the company's entire North Star is looking at how to monetize and really just use batteries in vehicles as an asset for communities, for fleet owners, businesses. And so, that can mean supporting the grid in real time from a vehicle to grid perspective. It can also mean, particularly in the US, where we have, issues with distribution grid reliability in some parts of the country, it can mean backup power as well. Here we're just kind of showing where we see the market. So, we think, right, this started with enabling charging of vehicles. How do we just get these vehicles on the road? And now we can do that for the most part, although I think folks operating large scale electric vehicle deployments would say that they wish, there's always kinks to work out. But we're good on that. Now we move into minimizing cost. A lot of our work focuses on minimizing the operating costs of vehicles, as well as minimizing the capital costs of actually installing the infrastructure, to really make sure that you don't have to spend $3 million on a utility upgrade and then whatever total cost of ownership you were expecting from the electric bus is out the window because of that big capital cost. So that's kind of a main focus of a lot of the work in the US, and I would say really where the center of the market is right now. And now we're also moving into this third phase, which is about capturing additional value. So vehicle to X use cases, right? That's the broad term, and glad Greg kind of called that out as an overarching term. Within V to X, there's various vehicle to building use cases, there's various vehicle to grid use cases, and I think one lesson I'll talk about at the end is how important it is to actually be really, really, really specific about what your use case is that you're trying to achieve, right? It's saying V2B is probably not good enough to actually design a project. So you really got to hone in on what's your goal, what makes sense at a site, what are you trying to achieve? From there, you can define your use case. So I'll get into that a bit more. Just a brief look at our projects across the US. This is an exhaustive, just highlighting school and transit projects relevant for this conversation. So the first case study I'll talk about is it's a microgrid project. So it's definitely obviously very related to resilience, but this is not a bidirectional project. However, Joe wanted me to touch on it. I do think it's an important example to show as we think about the topic of sort of EVs and resilience in general. So this is a project in Maryland, Montgomery County. It is operating. It's been operating for over a year. It's a transit depot. And here, I talked about use cases. So here the question wasn't, can we use these buses to back up a building? It was, how do we use these buses when the building doesn't have power, right? Or when the grid is down. So there's a 2.5 megawatt grid connection that's used, on the daily to operate these buses. And then there's a 6.5 megawatt microgrid, solar, battery storage, backup generator. You total all that up and you get 6.5 megawatts. It's a project developed by AlphaStructure, and our software connects the charging stations to the microgrid controller so that if the microgrid were to island, and you need to basically re-optimize the amount of power going to each bus based on the available power from the microgrid, which was different than what the grid was providing, you can do that and things will happen seamlessly. And these buses can operate no matter if the grid is providing power to the site or not. So I think this is super important because a lot of fleets, in addition to using their assets, to provide resilience to the community, they may need also to have resilience for their own depot. So we wanted to highlight this use case. Second use case here is a vehicle to building project in Oakland. This is actually also using transit buses, so a bit different than the school bus conversation, although that many projects with school buses underway as well. But this is looking at using transit buses to provide backup power to 2 community sites in West Oakland, specifically library and a community center. And really important, I think, to note in this case is that it's a grant project funded by the California Energy Commission. We're looking at using 2 different bus types, so both a hydrogen bus, fuel cell, as well as battery electric bus, both of which are connected to a standard CCS bidirectional charger. One innovation here is looking at the fuel cell bus, because that can provide longer resilience. But the manufacturer of these buses, New Flyer, is involved in the project because it's not standard that a fuel cell bus would have a plug for a charger. So there's a bit of an interesting setup here. But the idea is to prove out that you can create essentially a microgrid that's just a vehicle and a charger and a building, right? There's no other loads. So I think Joe might talk about the Mover project at some point. That's a concept distinct from this, where you have, sorry, I should say there's no other generation. So the Mover project has a bus. It'll have other generation to create a microgrid, and the bus is part of the microgrid. In this case, I think you could say that the bus is the microgrid. So just in these 5 minutes, I've talked about 3 different sort of resilience use cases. One is a microgrid providing charging for buses. Another one is a bus being the sole source of backup power for a building. And a third one is a bus being incorporated into a microgrid that has solar and battery storage that's providing backup to a building and sort of augmenting that. So just in that sort of, this topic period I've been talking, you can see there's a couple of different use cases, and it's really important to understand what you're talking about. To wrap up here, I think I wanted to share some initial lessons learned from the projects that we've been working on that are either deployed or in deployment, like the Oakland project. So I think the first is within vehicle to X. I think it's really important not to confuse vehicle to building and vehicle to grid. These are 2 things that it's not a continuum where you start with vehicle to building and then you move to vehicle to grid. We may get to that point, but from our experience right now, these are really two different technical and regulatory processes and tracks from the perspective of the utility. For something to be operating in parallel with the grid and following the grid, like vehicle to grid, that is one thing, and that they can support that. Maybe not everywhere, but it's like solar or something like that, and they're working on supporting that. Or they can have vehicle to building, like an emergency generator, and that's another thing. But to go back and forth between those things is a challenge that we've been working on in Oakland that we don't have an answer, right? Is can you go from charging or discharging to the grid when it's up to then also having the same charger be providing backup power when the grid is not up? Usually right now has to be 2 different systems. I know I'm running low on time here, so last lessons here, I would say, I sort of talked about this already, so I'll go fast, but rigorous use case definition is key for designing and building a project. So you really want to dive in and say, like, I know electric vehicles and resilience go hand in hand, but what does that mean to me and what does that mean to my site? And then from there, you can go implement something. And then I think the last thing that's just a note on the market is to scale this technology across the country. I think we're going to need more hardware options, more charger options than there are currently in the market, especially when you're looking at doing implementations that use open standards. So there are a few more options in the market that are proprietary sort of solutions offered by an individual company. But when you're looking for maybe the highest and best implementation, where you have equipment that's from different companies and it's all using open standards and you can change things out, you're a bit more limited in the chargers that you choose. So I think that's a challenge that the industry is dealing with, and charger manufacturers are scaling up. And I think the work that WRI is doing around mutual aid agreements is awesome, because that's a signal to charger manufacturers that, hey, there's a market here, there's demand for this type of use case, let's build a product to support that. With that, I will wrap up and pass it to Karina.
Great. Thanks so much, Sam. Thanks for walking us through those many use cases of electric vehicles and microgrids. Let me quickly, as a way to kind of intro Karina, I'll just chat a little bit about this Mover demonstration project. Mover is it's got a great acronym, microgrid opportunities, vehicles enhancing resiliency. And you heard Allison mention that there's a couple of the panelists today are working on this together. This is it's a Department of Energy funded project where we are we're looking to create a microgrid at the Y East Middle School in Hood River, Oregon, using electric vehicle batteries, but it's combining these technologies of solar energy, battery stationary storage, an electric vehicle, and then trying to make a microgrid that Karina will talk about that runs when the power is out. And we are 9 months into this project, this 3-year project. I'll show you timeline in just a second. The goals are to create a playbook on how to create a microgrid that includes EVs. We're already having lots of learnings on vehicle and charger interoperability with these microgrids. But there's so many parts of a microgrid. Helping a district electrify their fleets and get vehicles as its own challenge, and creating the workforce that can service both the buses and the chargers and the microgrid is another learning that we'll be featuring in the playbook. And the one other learning that we're seeing is that pilot projects like Mover, it can act as a catalyst to drive more electrification at a school district. Allison, do you want to say briefly how the Mover school buses have led to additional school buses for the district?
Oh, that's a really exciting story. So Kyle Russell is the transportation director in Hood River County School District, which is a rural district with huge distances, extreme weather events. And Kyle and I together applied for EPA funding, and he landed funding for 2 electric school buses. That'll be in addition to the 2 that we have through Mover. And we're also just applied to the state of Oregon through DEQ for 4 more electric school buses. You build a fleet out, and I'm especially excited that this particular fleet electrification is doing a vehicle to building project, because that is an ultimate value add. I'll stop talking. I could go on and on. I'll turn it back over.
Oh, that's great. Thanks. Here's just our timeline: 2024 doing a lot of the designs, 2025 the installation, and then 2026 to 2027 operation. But without further ado, I'm going to turn it over to Karina, give her 10-minute of presentation. Let me stop sharing and to talk about some of our learning so far on this microgrid. And then we'll take Q&A and maybe go 5 minutes extra so we get a full, robust Q&A. Karina, over to you.
Yeah, thanks. All right. Screen showing okay?
Yeah, looks great.
All right, great. Yeah, I know we're running tight on time, so I'll try and go through this quickly, but we've got some good juicy stuff in here. So quick introduction: TAE, we're engineering consulting firm, and then including that modeling and analysis work. And our specialty is kind of in the very high performance and very innovative sort of spaces, and so that's where pilot project microgrids come in. All right, so as Joe described, what is kind of unique about what we're doing on our project is that we are trying to merge all the things together. We want all the flavors. So we've got our building, right? We have an existing building that we're working with, and that's the loads that we're supporting. And then from that, we're layering in PV and stationary battery, which is kind of the more traditional, if there is such a thing as a traditional microgrid, the more traditional microgrid configuration. And then our unique element is, of course, pulling in the battery, as the other folks have talked about, is this idea of using, pulling in the bus as this idea of a mobile battery system. I think that Sam hit on the fact that defining what kind of the project goals are and the operations is really important. That was really one of the first things that we did on this project. Anytime you're doing a project, you kind of have to navigate between 2 sort of endpoints. One is, what is it that you dream is possible, right? And then what is it that your budget and your site can support? And somewhere in between the 2 is where your project comes out. And so in this case, in the site of our project, we have this existing school campus. And so we started off by looking at the existing school campus, but then kind of pulling back and thinking about what do we have resources for in terms of our system sizing? What do we have space for our systems? And what we really ended up concluding was that the backing up the entire site wasn't probably the right answer for this project. We also have, as we kind of peeled back the layers, we've got some pretty interesting existing electrical infrastructure on this site. We have some interesting utility services. We have multiple utility services. And so when we really kind of started to work through all these different details, what we ended up finding was that the gym, the existing gym, actually lended itself really well to being sort of a resilience hub that we were trying to create. It has its own utility service. It is electrically isolated from the rest of the campus. It is actually physically isolated from the rest of the campus as well. And then it obviously provides a really good space for any sort of emergency responders or community meetings and things like that. And so that is what the system ended up being designed for, is using the gym as sort of our resilience hub that we were backing up. Project site, as you can see here, again, like I mentioned, the gym is physically isolated. It's also really well situated around transportation aisles. So we have the ability to drive the bus up to it, which obviously we want to do, get proximity and getting all of our equipment together. Luckily, we're not super space constrained as we would be in maybe some more urban environments. So we do have room for stationary batteries and then any supporting infrastructure like a switchboard and a transformer that we would probably need. And we're also located kind of nice near some existing parking that lends itself very nicely to some carport canopies for PV as one of our generation sources. We are showing possibly putting PV on the roof here, but that is something that we're still continuing to evaluate and will as we go through design. One of the interesting challenges in working with existing buildings, right, is you have to start thinking through the structural capacity of the roofs. This is a part of Oregon that can have really major snow events. And so there is some question of whether or not it can handle snow and PV and whether or not that's the right thing. So that's some of what we're working with as we continue to move through the project, is figuring out, where do we want our equipment as we move forward. All right, so with those as sort of our design constraints, right, we know what our loads are, we know what our battery size is, we have a general idea of how much PV we can probably do, and then we of course know our bus size. We put everything together into the models and started to see, all right, with all these conditions, what does this mean from a resilience operation, right? How many hours of operation do we get out of this system with the existing building? And I'm going to talk on that existing building piece in a bit, because the existing building systems was one of the plot twists, I would say, we found in the project here. So what we found is that, stationary battery alone supports the building at a pretty consistent rate year round. I'll talk a little more on the building systems here. Currently, electrical service for this building supports plug loads and lighting, and so that's why it looks like a really nice flat load profile there, if there's any energy modelers in the audience. When we add on PV, obviously that gives us that ability to recharge that battery during the day and then discharge it again at night to support loads. This is in a part of Oregon that is not nearly as rainy as Portland, and so they get really beautiful sunshine much of the year, and that really did help kind of increase that resilience, particularly in the summer. And in this particular site, when we think of what are the resilience conditions going to be, it's most likely going to be sort of either in a winter scenario, in which case we likely won't have a lot of PV production. We probably are going to have snow on the panels kind of a situation. And then the summer, we unfortunately in the Northwest now have a wildfire season. And so summer outages are one of the main concerns that we were dealing with, particularly in this part of Oregon. They'll often have a lot of the wildfire responders will be stationed out of this area. And so having that extra boost in the summer, which we see really significantly increases the operating time, is actually super valuable in terms of creating that resilience for the site. And then the last one here, we added in the bus, and obviously that helps boost the whole thing up, right? Because we've just added additional storage. And then again, we have that ability in the summer to run, longer with the combination of all three resources. So that brought us to kind of what our current working basis of design is. We are still very early in our design work on this. This is kind of a schematic design level one line. We have a lot of work, a lot of adventure still in front of us here as we move along. I'm sure Joe and I will be back throughout the years to tell tales of adventure. Key things to kind of note on this one line is that we did also include provisions for a temporary generator, just to kind of add a belt and suspenders to our belt and suspenders from a resiliency standpoint. We also have provisions for additional batteries in the future as battery prices start to come down. Wanted to make sure that the client had the option to continue to add batteries if they wanted to again keep moving that resilience operation line up. Probably the biggest thing to note about this, though, is maybe there's two elements to it. One is that we did determine that it's going to need a new electrical service. And this is something that we run into in a lot of cases with microgrids on existing buildings, is that there's a lot of really interesting stuff out there in terms of electrical infrastructure, utility services, stuff that's been in place for 50 years, 70 years, right? And is needing an upgrade for various reasons. In this case, the existing service is a pretty unusual one. It's a high leg open delta, which is more what we see in kind of agricultural applications. And when we went through and did sort of the power quality and power stability studies, we basically came to the conclusion that it would be nearly impossible to run a stable microgrid system on that as a utility service. And so we would have maybe the resilience option, but we wouldn't have the grid connected, which is very much part of what we're trying to do on this project for the PV and the battery pieces. And so what that's leading us to is needing to have a new utility service and then a fairly extensive switchboard to support that. Okay, so I'm going to take a little bit of a plot twist here, and I'm not going to talk about buses anymore. Part of the reason for this is, one, like I said, we're still in the really early phases of the design, and so some of the main lessons learned we're still working through ourselves and figuring out how this design is going to come together. The other part is that the plot twist is a true story. This was a plot twist for us as we got into the project and started again peeling back the layers of the existing systems and found that there were a lot of elements that needed to kind of be addressed before we even got to the part about talking about buses and microgrids. And the reason Joe and I wanted to talk about this today is that we find this to be actually really common in microgrid projects on existing buildings. And so we wanted to sort of embrace that, because when we look to how do we move from pilot projects to wide scale deployment, I think there's a tendency we want to kind of focus on the cool tech and the new innovation of microgrids. But in a lot of ways, one of the main barriers we have to overcome kind of as an industry for wide scale deployment of microgrids is the less glamorous, kind of boring, but super important stuff of utility transformers and existing building systems and switchboards and that kind of stuff. And so we wanted to touch on that today, because we felt it kind of linked into this larger conversation. So the first one that we dealt with was the existing building is a dual fuel building, which is pretty common in the Northwest. So we have our lighting and plug loads is on electric, and then our heating and our hot water is on natural gas. And so the first question was like, well, shouldn't we move the building to all electric? So that way everything is on the microgrid. And that led to some good conversations within the team, as well as questions that came in from the community and some of our open forum community events for this project of like, well, but isn't it better to have the redundancy of having two different systems, right? So if the utility goes down, the electric utility goes down, you still have natural gas heating, don't you want to keep those separated? And I think the reason we want to touch on this today is that this is actually a very common question that comes up in projects that have dual sourcing and are looking at resiliency. And the way that we think about it on this project, and really in any resilience conversations, is that that redundancy of natural gas isn't necessarily a guarantee of resiliency, right? Historically, we've seen less maybe outages from the natural gas side because of the fact that more of it's underground, whereas electric utility tends to be overhead. And so you're more susceptible to weather events and trees and that kind of a thing. But they are still both grids when you think about it, right? They're these large, external, complex systems. And if something goes wrong upstream in the system, right, the site itself does get impacted by it and doesn't generally have a lot of control over how to fix it. The other piece of it is that the idea of the natural gas systems being more reliant on the grid we're starting to see that not be as true anymore, at least in the Northwest regions. When we're seeing the major events that are affecting the grid in the winters and in the summers, we're now starting to see them also affect the natural gas grids as well. And so both of them are starting to struggle. And so what that really brings us to is this kind of a different definition of resiliency, of not just saying redundancy, but looking at redundancy and self-reliance, right? And so when we look at self-reliance and say, well, what is the energy source that can be self-reliant? Electricity is the one that can be self-reliant because we can generate it on site, right? And so that is, again, pushing us towards that if we really, really want to get this site so that it is fully self-reliant in terms of its resilience, one of the things that we need to look at is what would it take to convert that existing natural gas heating and hot water system over to electric, so that way we are able to support all of it with our on-site resources. So with that in mind, we did look through, kind of took a little bit of a side quest and said, all right, what would it look like if we converted the entire building to electric? The other thing to note is that the existing building does not have air conditioning, which is a problem in the summer. And so it would add that additional layer of resilience operations by adding air conditioning, by switching over to a high performance, high efficiency heat pump based system. What was really interesting when we did the analysis on this is that we found that not only do we get that additional benefit of cooling and resilience, we also found that because the existing building is kind of a funky system, there's actually really strong opportunity to just improve its overall efficiency and performance. And so one of the things we were concerned about is that if we move to all electric, would that increase operating costs for the school by having higher utility bills? And what we ended up finding is that it actually resulted in operating savings because it was so much more efficient. And so it really is sort of this like win-win-win of improved resilience, improved efficiency, and then improved operating costs. When we look at that from a resilience perspective, right, the question was then, okay, well, does this increase what our microgrid needs to look like? The answer was generally no. Again, there was such an improvement in efficiency that we were able to add kind of all that additional electrical load and still stay within what our operating was, our operating budget from our battery. We did find that there would potentially be some days of the year where we would want to supplement with a diesel generator. But again, when we looked at it as the whole, it still felt like it was really the right direction for us to go in. So where does that leave us as a project? So, you know, resiliency, it's a journey, not a destination, right? And it's a process. And so, you know, at a bare minimum, our project, we will be able to provide that lighting and that the plug loads is the intent with the system. The project, because the results from that electrification were so compelling, the project is trying to see if we can, you know, shake some change out of the couch cushions and find a way to help the district do that electrification work as well, so that we really can get that full kind of energy resilience of all building systems. And then the hope is that long term, that then sets up the community and the county to be able to continue to add layers of resiliency to this site by thinking about water resiliency and food resiliency, and really turn this into a hub for the whole community to be able to use. So I know we're at time. My main takeaway, existing buildings are hard, microgrids are hard, but we do got to figure out how to do both of them. So that's kind of where we're heading with this. So with that, I'll hand it back to you.
Rita. Thank you so much. That was a fantastic overview of the Mover project and some of the adventures, as you say, we've had so far on that project. Encourage our other panelists to come on camera. And Allison and I will ask a couple questions, and we'll probably go an extra 5 minutes since we have such great presenters and presentations. So I guess I'll start us off. Quick question that we got in the Q&A. What does the infrastructure look like to connect the vehicles to buildings in a microgrid? I know we've been in the weeds in the Mover project, but is it just a matter of getting a charger and plopping it down and voila, you can connect to the building? What does it look like from an infrastructure perspective to merge these two technologies? Why don't we start, Sam, why don't we start with you from the charter side?
Yeah, sure. So I can talk to the specific Oakland project, and again, that use case is no other distributed energy resources, just the bus, the charger, and the building load. So for there, you're looking at a transfer switch to isolate from the grid. I believe that site's going to be manual. There's a critical load panel, so there's only certain loads in the building that are being supported. The charger itself needs to be a bidirectional capable charger. It also needs to have an inverter that's capable of setting voltage and creating a microgrid. And it needs to have what called a black start module, but basically when the grid goes down, some way to sort of repower on the charger initially, and operate some of the background systems, and then the bus and the charger. So that's sort of physical infrastructure as far as my understanding, and then the bus and the charger are going to have certain software compatibility to be able to exchange messages, to say, okay, now it's time to discharge energy, and things like that. So that is, I think that's a brief summary.
Thank you, Sam. I am trying to find some questions that will have kind of wide applicability. And so I'm going to use this question to build some intuition around the potential impact of V2X. How many homes could be powered with critical loads, for example, AC, for one day by a fully charged bus? Looking for a rough estimate. Who would like to field that one?
And Karina, maybe I'll even pick on you for a sec. I mean, as far as the mover project goes, does the battery from this one bus, significantly, will that add a lot of storage to our to the microgrid there in Hood River, or what does that look like?
Yeah, I mean, what we found for our project, and this is not quite quantified in the terms of homes, but I would say it actually added a little bit more than we were expecting in terms of the support for it. And it gets down to, I think, as Sam had said, like, you got to define what your boundary, what are you trying to support? So it's the larger your loads, right, the less that the battery supports. But we actually were, I think, happy with where it landed, in that it did make a meaningful impact, we felt, in terms of extending the duration of the loads for it. And it is sort of that question of, yeah, you could have just done it by increasing the size of the stationary storage, but by getting that dual purpose, right, it didn't put that cost burden on of having something that is maybe sitting there the rest of the time. So I don't know if that doesn't specifically answer the house question, but we did find, at least in our gym context, it provide a meaningful contribution, we felt.
I think to my answer to this is just frame that slightly differently, because in this, and I could probably do math offline about the houses, and maybe we can email that out, but like vehicle to grid, right, where you're discharging to the grid in an emergency situation, that might go towards powering a house if it's a school bus, right, because it's just sort of sending out into the neighborhood when the grid is overloaded, throughout a whole territory. The electrons, might back up to a house. For what we're talking about with vehicle to building, it's specifically like you're matching a bus to a specific site that has specific known loads. And so I think for the Oakland project, it's the battery electric bus can provide roughly 6 hours of backup to the critical loads in the library, and the fuel cell bus maybe 11. And that's just a single bus. AC Transit has, I don't know, 1,000 buses, maybe more, some much larger number than that. And so, that could add up, even if you're only using a small percentage of the bus, maybe you're getting to, a small percentage of the total buses, you might be getting to, multi-day backup of a single, community facility.
Perfect. Thanks so much for that, Sam and Karina. Okay, my question next is, what are the biggest? We like to say there's cutting edge and there's bleeding edge, and maybe we define this as bleeding edge. And what are some of the biggest pain points that y'all have seen so far? I mean, where are the areas that need most development, either technologically or Robert, in mutual aid agreements? Maybe starting with you, Robert, if you have any thoughts. What are the biggest pain points you've seen from a bird's eye perspective?
Yeah. I mean, I think there are kind of two places my thoughts would jump to. One is that there's a lot of money out there for projects like this, but it takes a lot of knowledge to get at that money. Right? These tend to be really high capital investments, and so if you're just trying to dive into this, it's difficult to kind of parse that apart. And I'm glad we have webinars like this to start to talk about that, point people to things like Mover, point to the ESPI. The other part I think is echoing a point that Sam made earlier, that there's kind of a concern right now there's not a ton of supply in the market, and that supply maybe is not being driven by kind of a lot of perceived demand, right? And so if you have more projects like this, have more interest in this, where you're going to see like, hey, folks are out there and they want open source VDG capable chargers, you're going to start to see more open source VDG capable chargers on the market, and that will really kind of start to crack that nut open. Yeah, I'm curious to hear others thoughts on that.
Green or Sam, any thoughts on pain points from your perspective?
Yeah, all of the points are pain points. I mean, from an engineering standpoint, all of this is still pretty new stuff, and we find on every microgrid that we do, regardless of any well-intentioned promises that the products are ready and the technologies are ready and the site is ready, it always ends up being just a lot of like roll your sleeves up and just kind of have to creativity, engineering, kind of get your way through it. And same thing for commissioning as well. And so then adding in this additional one. So if we say that microgrids themselves are already, I wouldn't call them bleeding edge, but they're definitely still leading edge, right? And then we add in the piece of the electric, vehicle buses, and then the chargers for that. And then we're not doing the V to G, but we're doing the V to B, but then we're also trying to engage it with everything else. I mean, everything that I just said in that sentence is a new concept, right? And there's, you've kind of seen the pilots here. There's not a whole lot more of them out there, and all of them are having to work through it. And so it's from everything from just the equipment into the controls, into how does everything talk to each other. All of that's very new. And so it is very much a, exploratory kind of process. But the hope is that as we go, all of those good lessons are feeding back into the industry, and we are starting to move towards consistency in standards, consistency in products. One of the other ones is that's not even just on the microgrid side, but consistency in the utility interconnections. What we're finding with a lot of microgrid projects, and I think also in the V to G kind of stuff too, is that the utilities are also trying to figure out what does this mean for their systems, and how are they comfortable with them connecting and interconnecting. And so there's a lot of variation in what the interconnection requirements are. And so as more of these come out and they start to become more established, getting some, I think, coalescing around approaches within the utility industry of what the interconnection is going to look like, is going to help a lot as well.
Greg, do you want to?
Yeah.
Yeah, I wanted to just.
Okay.
Maybe
Sorry.
Greg, just add real quick, Allison, for our next.
Yeah, I just wanted to jump in real quick that, there's some other considerations too, which is, for example, battery degradation on the vehicle. That's still a huge concern. It's still a huge concern by OEMs. So there's a lot of other things in addition to the technology around the V to G or the V to X aspect, which is discharging back, for some purpose. But there's also huge parasitic loads. So every time you're running you're running through an inverter, you're losing a percentage. And sometimes that can be as high as 25% when you're doing total site management and you're running this through many different inverters. You're running it to stationary storage and then out of stationary storage and then to site AC power and then through the inverter system for the vehicle itself. So these all need to be these are all little points of consideration that need to be included in the planning process, and in addition for awareness. So, and getting the vehicle, the OEMs being able to support it. So there's still a lot of things that we're doing. I think that's where a lot of grant funding is coming in. Nobody wants to be the first to go. There have been some bad experiences, so we want to try to minimize those and push forward. There's a lot of potential. There's a lot of great work that's being done. But nobody wants to be the first one in. I guess it's kind of one of those things.
Thanks, Gregory. That's helpful. Here's a good nuts and bolts question. What is the infrastructure required for connecting to the building itself?
I think we touched on this earlier. I ran through example, right? The best of my knowledge at the Oakland project, and I'm happy to follow up with folks. I can talk to the engineer on my team who's working on that to share more that we can share about the exact setup. But you're going to need transfer switch, bidirectional charger, and a black start module to power that charger on if there's no other resources. In the mover project, for example, you have other energy sources that can power the charger. So maybe you can speak to that, Karina, because I just talked about the other project already.
Something that I learned on the mover project is that the charger itself, it has to be a bidirectional charger from the beginning. You can't take a normal charger and then go back in and mix. So you have to be intentional with your charger from the beginning if you want to end up with vehicle to building or V2X.
Yeah, and I can speak to it because we are connecting to the building. So in that one line that I flashed up kind of there briefly, we are setting it up as basically a microgrid distribution board. And so we're bringing all of the microgrid generation and storage resources onto one shared bus. So we have the stationary battery, the PV, diesel interconnection if we need that temporary generator, and then the EV charging all comes into that shared distribution bus. And what that allows us to do is we're not using a transfer switch on ours because we do want to have the ability to operate that in both a grid connected and grid disconnected mode. So we're not switching from one source to another per se, but it's more that if in the event of a utility outage, we have kind of a relay at the beginning of the switchboard that opens up as a switch, but not a transfer switch. So it's essentially disconnecting us from the utility, and then we're able to run behind the relay. We're able to run as our own isolated grid, and then when utility connection comes back, then we close back in and we reconnect into the grid. Is the approach that we're taking on Mover.
Perfect. Thanks. Well, so maybe for a final question, because we're a little over, but I'd like to hear from all the panelists. We did have a question talking about how vehicle to building and vehicle to grid are going to be becoming more standard, or maybe already getting more standard in the regular electric vehicle marketplace with all the vehicles coming out. Talk to us about how we get the resilience projects like we've been hearing today with electric school buses and microgrids. How do they go from pilot stage to becoming standard over the next years and decades? Maybe we'll start, why don't we go in order of presentations? We'll start with you, Greg.
Sorry, I was having trouble getting off mute. Real quickly, and we're working with a lot of the panelists here already. So I think it's capturing the learnings from, and that's the good, the bad, the ugly. It's, documenting these things, documenting the special circumstances. What we want to do, especially to scale up, we need to take this from being a one-off and a special circumstance to being able to be implemented across the board. And that is really kind of capturing what was done, what was the interaction with the utility, how did it get handled, how was the service connection or the interconnection application, what were the pinch points for the utility, what were the pinch points for the site host, and everybody else involved. When you're looking at doing this, you are looking at probably 10 partners in this space that all need to work together. And that's from the charger manufacturer to the solutions provider to the utility to the controller manufacturer to everybody. So it's capturing all these things, documenting, and also looking at those things that can be done concurrently as opposed to sequentially, to lessen the time frame. Because right now, a lot of these projects are taking huge amounts of time. We need to reduce them. So,
but Joe, could I go next? Because I have I have to drop off here in a second. Apologies. I'm getting pinged. But sorry, Bobby, I'll be really fast. I would agree with Greg, right? It's like everyone has one experience from the one pilot that they did, and the utility gave them very specific answers. And it's hard to know if that translates to a different part of the country with a different utility and different engineers. And so sharing learning so that there can sort of be like a shared pool of knowledge, I think is super important. I think beyond that, like it's the US, like capitalism, all of that, like you need market signals. So like the more compensation mechanisms there are for vehicle to grid, which are popping up around the country, but they're not everywhere. And then this mutual aid work, right? The more demand that industry sees for vehicle to building, the better. Because right now I think you see people willing to pay for vehicle to building, vehicle to home, and residential. But in commercial, people always ask us, like, well, who's paying for this, right? And probably maybe it's the county emergency services office, but that's not defined, right? And so kind of goes into my last point, which is that, like, getting to open standards, right? So getting to a place where the bidirectional operation of the charger to the bus and the charger to the control software is something that is common across multiple manufacturers, so that if you're a customer, you're not just like at the behest or beholden to like one company doing it one way, which could work really well. But then if that company disappears, then you might be stuck. So to get to that point where it's a much more plug and play thing, and it doesn't have to be designed custom for every site, you're going to need compensate. You're going to need some, like, companies need to be chasing money, or else they're not going to mobilize their engineering teams unless they're like a really, good meaning company out of the, goodness of their heart to like build something new and do open standards instead of just doing the way that they've been doing. So I think there's this sort of push and pull between like the demand for it, who's going to pay for it, that is sort of challenging. And so, that's perfect. That's government funding. That's why DOE is funding the Mover project. I assume that's why California is funding our project, right? Is like government coming in where there's this issue of like private industry covering the use case. So I think those would be kind of my points in terms of scale.
Thanks, Sam. Appreciate that. And feel free to drop. Thank you for staying extra.
Yeah, I'd also say for folks, if we didn't get to your question, Q&A, at least I'm happy to answer offline. So moderators, if you're putting those questions together, I'm happy to do some written answers for folks.
Sounds great. Yeah, we'll do that. Appreciate that. Great. Robert, next to you.
Yeah, I can jump in it. I think Sam hit a lot of the points that I would hit, and that's demand. And right, the folks procuring school buses, folks procuring other chargers and whatnot, getting the information in front of them that, like, if this is even a consideration, you need to be sure that you can have this capability on your bus, on your charger, and creating demand for that is going to induce manufacturers to make it happen. And when that happens, you can have a lot more of an open conversation, and hopefully there are few issues between each of these different stages if everything can talk together a little better. But yeah, Karina, if you want to jump on.
Yeah, I very much agree with what everyone said. So what I will add to it is that existing building or just existing infrastructure challenges of it. The reason I do really like the Mover project is because of the fact that it shows the very real world messiness that most are. That's one of the challenges sometimes with pilot projects, is that when you pick that really, really perfect site, it isn't necessarily uncovering some of those, again, less glamorous, but just as important challenges of how do you even get the site ready for a microgrid. And so that to me is figuring out, from program standpoints and whatnot, how do we make sure that there is, in addition to the funding for, again, all the kind of the cool tech, how do we make sure that we also have ways to support these projects with just sort of the infrastructure upgrades that are needed to make sure that we've opened up the path to then integrate all the cool tech.
Yeah, that infrastructure upgrades are so crucial, as we're learning. Thank you, Karina. Thanks, everyone. I know we've gone way over. Really appreciate the discussion. Huge thanks to our panelists. Allison, thanks for the great co-moderation. And we'll send out recording and slides very soon. So have a great rest of your day.
Thank you.
Thanks.